Welcome to this problem-solving session. In this video, we'll tackle LeetCode problem number 201, bitwise and of numbers range. This problem challenges us to explore bitwise operations and optimize our approach for a given range of numbers. Let's dive in and break it down step by step. In this problem, we are given two integers, left and right, which define a range of numbers, left, right. Our goal is to calculate the bitwise and of all the numbers within this range, inclusive. The bitwise and operation works by comparing each bit of two numbers. If both corresponding bits are 1, the result for that bit is 1, otherwise, it is 0. For example, if we perform the bitwise and of 5, binary 101, and 7, binary 111, the result is 5, binary 101, because the first and last bits match in both numbers. The range is defined such that left and right are integers between 1 and 2*31,1, and the output will be a single integer representing the end result of all numbers in this range. Let's look at some examples to understand this more clearly. In the first example, the input is left equals 5 and right equals 7. The range of numbers is 5, 6, 7. First, we write these numbers in binary. 5 is 101, 6 is 110, and 7 is 111. To compute the bitwise AND, we first compare 101 and 110, which results in 100. Then, we take this result and AND it with 111, which still gives 100. Converting 100 back to decimal gives us 4, so the output is 4. This demonstrates how the bitwise AND effectively zeroes out bits that differ across the numbers in the range. Now, let's examine another example. The second example involves left equals 0 and right equals 1. Here, the range of numbers is 0, 1. Written in binary, 0 is 0, 0 and 1 is 0, 1. Performing the bitwise AND operation on these numbers, we compute 0, 0 and 0, 1, which results in 0, 0. Converting 0, 0 back to decimal gives us 0. This highlights an important property. If the range includes 0, the end result will always be 0 because any number ANDed with 0 will result in 0. Let's continue to another example with a larger range. For the third example, we have left equals 10 and right equals 15. The numbers in this range are 10, 11, 12, 13, 14, 15. In binary, these numbers are 10 is 1010, 11 is 1011, 12 is 1100, 13 is 1101, 14 is 1110, and 15 is 1111. To compute the bitwise AND, we start with 1010 and 1011, which gives 1010. Next, we end this result with 1100, resulting in 1000. Continuing, 1000 and 1101 is 1000, and so on through the remaining numbers. The final result remains 1000, which is 8 in decimal. This demonstrates how the AND operation progressively eliminates bits as the range increases. Now, let's consider the constraints and edge cases for this problem. The constraints of the problem ensure that left and right are valid integers, with left always less than or equal to right. The range can include a large number of integers, up to 2*31,1, which makes a brute force approach impractical. Instead, we need an efficient algorithm to compute the result without iterating through all the numbers. For edge cases, if left equals right, the range contains only one number, and the output is simply that number. If the range includes 0, the result is always 0. Additionally, for large ranges, most of the lower order bits will be 0 due to alignment, which can be leveraged for optimization. Finally, even the largest possible range, 1, 2 to the power of 31, 1, must be handled efficiently by the solution. To solve the problem, let's first consider the brute force approach. The idea here is straightforward. We iterate through all the numbers in the given range, from left to right, and compute their cumulative bitwise AND. We start by initializing the result as left, since it's the first number in the range. Then, for each subsequent number, we update the result by performing a bitwise AND operation between the current result and the number. Once all numbers in the range are processed, we return the final result. While this approach directly aligns with the problem statement, it has significant drawbacks. The time complexity is O(n), where n is the size of the range. This means that for large ranges, the method becomes highly inefficient because every single number must be processed. Additionally, many operations are redundant. For example, once a bit in the result becomes 0, it will remain 0 regardless of the subsequent operations, yet the algorithm continues iterating unnecessarily. This inefficiency makes the brute force approach impractical for larger inputs. Now, let's explore a more optimized approach based on a key observation about the bitwise AND operation. The result of the AND operation across a range of numbers is determined only by the higher order bits that are common to all numbers in the range. Any bits that differ at any position within the range will result in 0 at those positions in the final result. This means that the task boils down to identifying the common prefix, or shared higher order bits, of the numbers left and right. To achieve this, we repeatedly right-shift both left and right, effectively removing their differing bits from the right, until the two numbers become equal. During this process, we count the number of shifts performed. Once left equals right, the common prefix has been isolated. We then reconstruct the result by left shifting this common prefix back to its original position, using the shift count. This method is both efficient and elegant, as it avoids unnecessary computations and directly focuses on the core insight of the problem. The optimized approach has several advantages in terms of performance. Its time complexity is O, log, max, left, right, as the numbers are right-shifted until they become equal, which happens in logarithmic time relative to the input size. The space complexity is O, 1, as it uses only a constant amount of memory. These characteristics make it highly efficient, especially for large ranges. Additionally, by avoiding the need to process every number in the range, this approach eliminates redundant operations, focusing only on the critical bits that determine the result. Another alternative to this method is the use of bit masks to isolate the common prefix. Instead of right-shifting, we start with a mask that has all bits set to 1 and iteratively clear bits and right using the mask until left and right are equal. While this method achieves similar efficiency, it introduces slightly more complexity in implementation without offering significant benefits over the right-shift technique. For these reasons, the right-shift approach remains the preferred choice. After evaluating the different methods, we selected the optimized approach of finding the common prefix as the best solution for this problem. This approach stands out for its efficiency, as it avoids iterating through all the numbers in the range, making it much faster than the brute force method for large inputs. Moreover, it directly leverages the key insight of the problem, that only the common higher order bits matter for the final result. Its implementation is also straightforward and avoids the additional complexity of using bit masks. While the brute force method may be simpler to understand conceptually, it is impractical for large ranges due to its inefficiency. On the other hand, the bitmask approach, though efficient, doesn't offer substantial advantages over the right-shift method and is slightly more complex to implement. By balancing clarity, efficiency, and correctness, the optimized approach using right shifts emerges as the most appropriate choice for solving this problem effectively. Here, we are tasked with finding the bitwise and of all numbers in the inclusive range from left to right. Essentially, we take the numbers one by one and apply the AND operation across the entire range. The brute force approach directly implements this by starting with the number left and iteratively performing the AND operation with each subsequent number in the range. We initialize the result as left, then loop from left plus 1 to right, updating the result with the AND of the current number. An important optimization here is that if result becomes 0 at any point, we can stop early, since the AND of any number with 0 is always 0. Finally, we return the result after completing the loop. While this approach works, it can be inefficient for large ranges, which prompts us to explore an optimized solution later. To better understand the brute force approach, let's walk through an example with left equals 5 and right equals 7. The process begins with result initialized to 5, which in binary is 101. We then perform the bitwise and with 6, binary, 110, which results in 100 in binary. Next, we end this result with 7, binary, 111, and the outcome remains 100. Converting this binary result back to decimal, we get 4. This example demonstrates how the brute force method iteratively applies the AND operation across the range. However, as the range grows larger, this approach becomes computationally expensive. To address this, we use an optimized method that leverages the binary structure of numbers. Now, let's explore the optimized approach using the same input, left equals 5 and right equals 7. Instead of iterating through every number, we focus on the binary representations of left and right. The key idea is to identify the common prefix of their binary forms by removing differing bits. Starting with left equals 5, binary 101, and right equals 7, binary 111, we see that the numbers are different, so we right shift both by 1 bit, dividing each by 2. This gives left equals 2, binary 10, and right equals 3, binary 11, with a shift underscore count of 1. Since they're still different, we repeat the process, right shifting again to get left equals 1, binary 1, and right equals 1, binary 1, and incrementing shift underscore count to 2. Now that left equals right, we stop. To reconstruct the result, we left shift left back by 2 positions, restoring the common prefix and yielding 4, binary 100. This approach is significantly faster, as it avoids iterating through the entire range. The optimized approach is built on several key insights. First, in the brute force method, if result becomes 0 at any point, we can terminate early because the n of any number with 0 is always 0. Second, the optimized method works by recognizing that the n operation eliminates differing bits, and right shifting repeatedly removes the least significant bit until the numbers match. This avoids the need for a full iteration through the range. Additionally, edge cases like left equaling right are handled naturally, as the result is simply left. Large ranges, such as left equals 0 and right equals 10⁻9, are efficiently managed due to the logarithmic complexity of the optimized approach. Importantly, no extra data structures are required, as the solution operates directly on the input integers using simple variables like result and shift underscore count. Analyzing the time and space complexity, the brute force approach has a time complexity of O(n), where n is the size of the range, right-left. This becomes impractical for large ranges. On the other hand, the optimized approach has a time complexity of O log, max, left, right, as the right shifting process effectively reduces the range by a factor of 2 with each step. Both approaches operate in constant space, O(1), as they only use a few variables. In summary, the optimized method makes efficient use of the binary representations of numbers, achieving logarithmic time complexity by avoiding unnecessary iterations. This makes it the preferred solution for handling large inputs. The given problem requires us to find the bitwise n of all numbers in the range, left, right. Instead of using a brute force approach, which would involve computing the n for every number in the range, leading to inefficiency for large ranges, we can utilize the properties of binary numbers to achieve a more optimal solution. ###explanation 1. Key insight: the result of the bitwise n operation for a range of numbers is determined by the common prefix, most significant bits, shared by all numbers in the range. Bits that differ in any of the numbers will result in zeros in the final AND. 2. Algorithm: start by initializing a counter shift to 0. This will keep track of how many right shifts we perform. While left and right are not equal, repeatedly right shift both numbers by 1 bit. Each right shift effectively removes the least significant bit, narrowing down the range to its common prefix. Once left equals right, we have isolated the common prefix. Shift the result back to its original position by left shifting the number by shift positions. 3. Efficiency: the number of iterations is proportional to the number of bits in the range, logarithmic complexity, making this approach highly efficient. For example, consider left equals 26, 11010 in binary, and right equals 30, 11110 in binary. The algorithm identifies the common prefix 11,024 in decimal, after 2 right shifts and restores it by left shifting back, yielding the correct result. This approach ensures optimal performance even for large ranges, avoiding the inefficiencies of brute force computation. This is the Java implementation of LeetCode problem number 201, bitwise n of numbers range. The logic mirrors the Python solution by identifying the common prefix of the binary representations of the given range. Key differences include explicit type declarations and the use of Java syntax for bitwise operations. The algorithm efficiently finds the result in O, log, max, left, right, time by repeatedly right-shifting both numbers until they are equal and then left-shifting the result back to its original position. To solve the problem of finding the bitwise n of all numbers in a given range, we start by focusing on an example where left is 5 and right is 7. The goal is to identify the common bitwise prefix shared by all numbers between these two values. First, we initialize a variable shift to 0. This variable will help us track how many times we need to right shift both numbers to find their shared prefix. We then compare left and right. Since they are not equal, we right shift both numbers by 1 bit and increment shift. After the first shift, left becomes 2 and right becomes 3, while shift is updated to 1. We compare the numbers again, and since they are still not equal, we repeat the process. This time, left becomes 1, right becomes 1, and shift equals 2. Now that left and right are equal, we've identified their common prefix in the shifted form, and the loop terminates. Once we have the common prefix in the shifted form, the next step is to restore it to its original position. We achieve this by left shifting left back by the same number of times we shifted earlier, which is stored in shift. In this case, we take left, which is 1, and left shift it by 2 positions. This gives us a result of 4. Hence, the bitwise and of all numbers between 5 and 7 is 4. Moving on to a second example, where left is 0 and right is 1, we start by initializing shift to 0 again. We compare the two numbers, and since they are not equal, we right shift both by 1 bit and increment shift. After this operation, left becomes 0 and right also becomes 0, while shift is updated to 1. Now that both numbers are equal, the loop ends, and we've found the common prefix in the shifted form. With the common prefix identified, we proceed to restore it to its original position. In this case, since left is 0 and shift is 1, we left shift left by 1 position. The result remains 0. Therefore, the bitwise and of all numbers between 0 and 1 is 0. Now, let's consider a third example where left is 10 and right is 15. Again, we start by initializing shift to 0. The goal remains the same, to find the common prefix shared by these two numbers in their binary representations. To find the common prefix, we compare left and right. Since 10 and 15 are not equal, we right shift both numbers by 1 bit and increment shift. After the first shift, left becomes 5 and right becomes 7, while shift is 1. Comparing them again, we see they are still not equal, so we repeat the process. This time, left becomes 2 and right becomes 3, while shift increases to 2. Since they are still not equal, we shift once more. Now, left becomes 1, right becomes 1, and shift is 3. At this point, the numbers are equal, meaning we've found their common prefix in the shifted form. To restore this prefix, we left shift left by 3 positions, resulting in 8. Therefore, the bitwise and of all numbers between 10 and 15 is 8. The time complexity of the solution is O, log, max, left, right, and this is primarily determined by the while loop in the algorithm. Let's break it down step by step. First, the while loop continues until the left and right values become equal. In every iteration, both numbers are right shifted by 1 bit, which is equivalent to dividing them by 2. This means that the number of iterations is directly related to the number of bits in the binary representation of the larger of the two numbers, left or right. Mathematically, this is proportional to the logarithm of the maximum value between left and right. Since each iteration involves constant time bitwise operations, the total time spent in the loop is proportional to the number of iterations. After the loop, the common prefix of the numbers is shifted back to its original position using a left shift, which is also a constant time operation. Overall, the dominant factor in the time complexity is the while loop, giving us O, log, max, left, right. The space complexity of the algorithm is O(1), meaning it uses a constant amount of memory regardless of the input size. This is because the algorithm only uses a few scalar variables, shift, left, and right. These variables occupy a fixed amount of space in memory, irrespective of how large the range between left and right might be. Additionally, there are no recursive calls in this solution, so no extra memory is needed for a call stack. Similarly, there are no data structures like arrays or lists being allocated, which further ensures that the space requirements remain constant. Therefore, the space complexity is O(1). In comparison, let's consider the brute force approach to solving this problem. The naive method involves iterating through every number in the range, left, right, and performing a bitwise AND operation for each. The time complexity of this approach is O, right, left, because it requires one iteration for every number in the range. For each iteration, a constant time bitwise operation is performed. However, when the range is large, such as when right-left is close to a billion, this approach becomes computationally expensive and impractical. On the other hand, the brute force method still has O(1) space complexity, as it does not use additional data structures. Nevertheless, the linear scaling of operations with the size of the range makes this method far less efficient than the optimized approach. The optimized solution significantly improves upon the brute force approach by focusing on finding the common prefix of left and right in their binary representations, rather than iterating through all the numbers in the range. By using bit shifts to reduce the numbers until they match, the algorithm eliminates unnecessary computations and achieves a time complexity of O log max left right. This is a major improvement over the O right left time complexity of the brute force method, especially for large ranges. Looking deeper, the mathematical reasoning for the time complexity lies in the number of iterations of the while loop. Each right shift reduces the binary representation of left and right by 1 bit, and since a number with value n has about log 2, n, bits, the number of iterations is proportional to O log max left right. Each iteration involves constant time operations, including the final left shift, so the overall time complexity remains O log max left right. In conclusion, this optimized solution is highly efficient for handling large ranges of input values. By focusing solely on the significant bits that contribute to the result, it avoids the unnecessary computations inherent in the brute force approach. This efficiency makes the algorithm well-suited for scenarios where the range between left and right is large, as it reduces the computational burden while maintaining constant space usage. The combination of logarithmic time complexity and constant space complexity highlights the elegance and practicality of this optimized approach. When solving the problem of finding the bitwise and of a range, there are some common mistakes to watch out for. First, using a brute force approach to iterate through all numbers in the range, left, right, is inefficient, especially when the range is large. For example, if the difference between right and left exceeds a million, this approach becomes computationally expensive with its O(n) time complexity. Instead, optimized techniques like identifying the common prefix in the binary representation or leveraging bit shifting can dramatically reduce the complexity. Another frequent oversight is ignoring the impact of 0 in the range. If the range includes 0, the result is guaranteed to be 0, and failing to recognize this can lead to unnecessary computations. Adding a simple base case to handle such scenarios can save a lot of time. Finally, some candidates misinterpret the problem's constraints, assuming the range is small or the numbers are close together. Large ranges, such as from 0 to 2^31^1, or ranges spanning powers of 2, require scalable solutions. Always analyze constraints and test edge cases to ensure your solution is robust. Another common pitfall is overcomplicating the calculation. For instance, some candidates attempt to simulate the bitwise operation manually, bit by bit, using arrays or other data structures. This approach not only increases the risk of introducing bugs but also adds unnecessary complexity to the solution. Instead, you should rely on bitwise operators directly and focus on identifying patterns or mathematical shortcuts. Additionally, many fail to recognize opportunities for early exit. Once the result of the operation is guaranteed to be 0, for example, when the higher bits of two numbers in the range differ significantly, there's no point in continuing the computation. Implementing early exit conditions can save both time and resources, making your solution significantly more efficient. To tackle this problem effectively, it's important to understand some key insights. The bitwise of a range, left, right, is determined by the bits that remain unchanged across all numbers in the range. This is equivalent to finding the common prefix in the binary representation of left and right. A powerful optimization pattern is to use bit shifting. By repeatedly right-shifting both left and right until they become equal, we can isolate this common prefix. Once the prefix is identified, we can reconstruct the result by shifting it back. This reduces the time complexity to O log max left right. It's also crucial to consider edge cases, such as ranges that include 0, ranges with a single number, and ranges spanning powers of 2, like from 1023 to 2048. During interviews, clarity in communication is critical. Explain your thought process step by step, particularly how you identify the common prefix and why your approach is efficient. Logical reasoning and clear explanations leave a strong impression on interviewers. This problem is closely tied to several other LeetCode problems that involve bitwise manipulation. For example, LeetCode 190, reverse bits, requires reversing the binary representation of a number, which involves similar bitwise operations and shifting techniques. LeetCode 338, counting bits, focuses on understanding binary representations and efficiently computing bit counts for a range of numbers. Another related problem is LeetCode 461, Hamming distance, which emphasizes the XOR operation to calculate the number of differing bits between two numbers. Lastly, LeetCode 371, sum of two integers, involves performing addition using bitwise operations without relying on arithmetic operators. Studying these problems can deepen your understanding of bitwise manipulation and help you recognize patterns that are applicable across a variety of scenarios. There are several alternative approaches to solving this problem, each with its own trade-offs. The bitwise shift approach is one of the most common. Here, you repeatedly right-shift both left and right until they are equal, keeping track of the number of shifts. Once the common prefix is identified, you left-shift the result back to reconstruct the final value. This method is efficient, with a time complexity of O, log, max, left, right, but it may feel less intuitive to some candidates. Another method is the masking approach, where you use a bit mask to isolate the common prefix directly. This approach is conceptually similar to the shift method but can be implemented more compactly. Finally, there's the brute force approach, which involves iterating through all numbers in the range and computing the cumulative AND. While straightforward to implement, this method is inefficient for large ranges due to its O(n) complexity. Understanding these approaches and their trade-offs allows you to choose the best solution based on the problem's constraints and the interview context. Great job! To summarize, we solved the bitwise and of numbers range problem by leveraging binary representation to optimize our solution. Remember the importance of analyzing patterns in bitwise operations to save time and space. Thanks for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!